All right, so how do we find these things? Really is the question, right? So this is the what's going to be called the characteristic equation. So given this 2 by 2, let's find the eigenvalues. In other words, find all the lambdas such that a minus lambda I times x equals 0 has a non-trivial solution. That's what we're doing here. Or another way is like find all the lambdas such that a minus lambda I is not invertible. Same thing. So take a look at a minus lambda I, right? Looks like this. And it's not invertible if the determinant is 0, right? And we know the determinant of a 2 by 2 matrix. So I go ahead and calculate the determinant, right? 2 times this entry times this entry minus that entry times that entry. That's the determinant. And notice that I get a quadratic equation, right? That's what's starred here. Specifically, I want to know when the determinant is 0, so that factors very nicely. You're welcome. And it turns out lambda equal 9 and minus 5. So the eigenvalues of this matrix A are 9 and minus 5. This thing here, which is starred, is called the characteristic polynomial. Okay, so the characteristic polynomial will yield the eigenvalues. They're the zeros of the characteristic polynomial. Okay, obviously with a 2 by 2, you're going to get a degree 2. Okay, so those are easy enough to find. If you had a 4 by 4 matrix, that's going to be a degree 4 polynomial. Some of the roots may be repeated. We'll get to that later. But that is called the characteristic polynomial. Like it says here, be careful. Row reduction is used to find eigenvectors, but we don't use that to find eigenvalues, since the echelon form usually doesn't display them. Okay, so we find the characteristic polynomial, and we look for the zeros of that. That's what gives us the eigenvalues. So here we're just finding characteristic polynomials, right? So it's just based on looking at a minus lambda I and specifically looking at the determinant. When is the determinant equal to 0?